Okay, today I'm going to discuss about different types of acoustics boundary condition available in Ansys Mechanica. When somebody is setting up acoustic analysis, one can see various types of impedance boundary condition in different names. Something like impedance boundary, absorption surface, radiation boundary, impedance sheet, and transfer admittance matrix. All of these boundary conditions in some or other way kind of mathematically mimic the impedance of a particular surface or a particular medium. To kind of start with, let's take an example. We have two mediums of fluid. Let's say this is a kind of a duct where there are two mediums inside this. Let's say, okay, this side there is medium 1. I'm sorry. Let me make this. This side it's medium 1. And this side it is medium 2. Now imagine that there is a acoustic wave. Imagine for a simplicity, it's a plane wave, acoustic wave coming this side, and this medium is going to have some density, let's say ρ1, and some speed of sound c1. And this medium is having some other density and some other speed of sound. This means that the impedance of this medium is different from the impedance of this medium. Okay, you can imagine this is a air and this is a water. Now, when this wave come and hit this interface, due to the difference in the impedance of these two medium, what's going to happen is that out of this incoming wave, some amount of wave get transmitted to this medium and some amount of wave get reflected into the same medium itself. This is how the incoming energy of the acoustic wave get distributed. And there is another possibility is that the some amount of energy get dissipated due to in this case it won't get dissipated, but assume that at this place there is a instead of this as air and water, assume this is air and this is acoustic foam. If you assume this is a foam, then what would happen? Some amount of energy will get reflected back, some amount of energy will flow through this foam, some amount of energy will get dissipated. There are three mechanisms exist in this place. What possibly how this incoming energy can redistribute. So all these three boundary condition depend. All the boundary condition depends on at what situation we are going to model the impedance. Say this impedance boundary to start with. Oftentimes we usually get the acoustic performance of any acoustic material commonly in a commercial language in terms of the absorption coefficient or transmission loss, something like that. But mathematically, to use this any computational program, everything need to be converted into a impedance form, right? So the impedance has is a complex number. It has two parts, the real part and imaginary part. And there also a relationship exists between the reflection coefficient or absorption coefficient alpha and the real and imaginary part of the impedance. Say for example, for a given medium, assume this is a air, once we know what is the air density and the speed of sound, and if we know what is the real and imaginary component of this complex impedance term, we can use this relationship to calculate what is the reflection coefficient and absorption coefficient. When we physically test any acoustic material for its absorption or a reflection capability, the fundamental quantity we measure is the impedance, but they are in turn converted into a common designer terms, rather analyst terms, something like a reflection coefficient or absorption coefficient and so on. So coming back to this, there are different ways where this the mismatch in the impedance can happen. When I say the mismatch in the impedance, like either air coming and hitting a foam, or the air passing through a different medium which is having different impedance. Basically, that's the idea. So now here, when the impedance is characterized by we can say impedance jut as the impedance jut is nothing but the ratio of acoustic pressure and the acoustic velocity. That's the impedance. So now if we kind of look at this case, the air coming in here, now what is going to happen is at the moment it start coming out, it opening to the biggest domain. So the velocity and the pressure are going to change such that the impedance is going to change here when the duct opens to the atmosphere. The another possibility is that the wave comes, but here is a rigid wall. On this wall, the velocity is 0. Okay, so there is an impedance change. Impedance is basically a function of both frequency and the spatial location. So here is the impedance change. Now let us look at this scenario. There is some perforated, micro perforated plate or something. When the wave comes here, it is not a situation of the pipe opening to the atmosphere or the closed air. There is a partial flow of the acoustic waves. Then in this case, the impedance is different, for instance. Now look at this case where the wave comes in, but it is not hitting the rigid material like this end termination, but instead assume there is a small amount of foam as a sound absorbing material. So in this case, the impedance that the wave is going to see at this discontinuity is different. So now the sound distribution, if we want to start measure the sound distribution at this point in all the scenarios at the same location, it will be different in all of these cases. In all of these cases, it will be different because of what the impedance that the traveling wave sees. So now in these cases, as you can see, in all these cases, the impedance change happens at the exterior surface of the geometry that we are going to analyze. Now imagine a situation here. Imagine a situation of this where the acoustic wave is coming here and it is seeing a change in the impedance because of this foam, and then it continued to travel. So now if you want to model the acoustic wave propagation, something like this, something is going to happen here, then it will continue to travel. Okay, so we need to model this entire domain. But in all other cases, our acoustic wave come and stop at this end. Okay, so we need to mesh only up to this end. We don't want to mesh beyond this. But in this case, the the medium which is either going to observe or reflect, whatever it is going to do, is somewhere inside the acoustic domain. Okay, so coming back to this, these three boundary conditions, the impedance boundary, absorption surface, and the radiation boundary, can be used only if the impedance change occurs at the exterior surface of the acoustic domain. These two boundary conditions, that is these two boundary conditions, that is the impedance sheet and the transfer admittance matrix boundary condition, can be used when we need to model some kind of impedance somewhere inside the acoustic domain. Say, to give an example, let us take this situation. There is a duct, the air is coming inside this, and this carries some amount of acoustic energy. Now in between we are introducing a screen, okay, which is expected to change the impedance or do something. So what and all it can do, it can do three possibilities as we explained earlier. One, it is going to transmit only some amount of the incoming acoustic energy. It will also reflect some amount of the incoming energy back, and also it can dissipate some amount of energy as a heat or something. So this can be anything. Like imagine that in automobile we have a filter, a paper filter. This can be a paper filter, or this can be a kind of a small perforated plates with a lot of holes like this. Okay, or it can be a small block of foam, the small block of a foam which is kept in between the duct. Okay, for various reasons. Now there are multiple ways to model this. The one way is that, now assume a scenario of a thin wire mesh. So if you want to actually go and mesh the thin wire mesh, it is going to consume a lot of elements and so on. So in general, to model these kind of thin structures, normally we don't go messing the geometry of those smaller elements. Instead, we will characterize these as using some kind of a impedance form. Again, to understand this, this is very clear now. When to use these three boundary conditions. These three boundary conditions can be used for a scenario where we want to model the impedance at the end of the mesh. But if you want to model somewhere in between, there are two scenarios, as I said. One is the impedance sheet boundary condition, and another one is the transfer admittance boundary conditions. The difference between these two is that in transfer admittance, it is assumed that the velocity is continuous before and after that object. So if you are talking here, there is a wire mesh, or it can be a foam, or it can be a micro perforated plate, or whatever it may be. This is something like the entry point 1, and this is the exit point 2. So it is assumed that the velocity is continuous across this plate, and only the pressure is discontinuous. In the impedance sheet boundary condition, it is assumed that the pressure is continuous across this boundary, but there is a change in velocity across this thing. So first, depending on the type of the absorbing element that is being used, we need to decide should velocity is continuous across the sound absorbing object, or pressure is continuous across the sound absorbing object. So based on that, we have to go with either one of this. Now, once we kind of decide what is that, first let me explain the impedance sheet. Once it is decided that we have to go with the impedance sheet, then what we have to do is select one of these surface where we are going to model this. Let me hide this. Let me bring this back to shaded exterior edge. Let me hide this body, select this face, and provide what is the resistance and reactance part of the impedance. As I explained earlier, the impedance is a complex part which has a real part as a resistance and the imaginary part as a reactance. So we have to specify the real and imaginary part of the resistance and reactance. That is clear. Then everything else is taken care. When we are coming for a transfer admittance matrix, we need to provide basically a matrix. What is this matrix is about? Let me kind of explain here. So now, as I said, there is a incoming acoustic wave. The incoming acoustic wave is characterized by two quantities. One is the acoustic pressure, and the second one is the acoustic velocity. So when this crosses this absorbing element, then the P2, there is a change in pressure, there is a change in velocity. So we are going to talk about these four elements. What is happening among these four before and after that particular element? Okay, so there is an input energy, some amount of energy is transmitted, some amount of energy is reflected. So now there are many possible scenarios that can happen. One, let's look at these two side by side. Let me also bring this back here. Okay, now what can happen among the some energy that is coming in? Let's say this is my one incoming in, this is out. Let's say this is port 1 and port 2. And among the some energy coming in here, some energy is getting reflected back. Okay, so this is a 4x4 matrix. So some energy is reflected back. That represents when the in S11. Okay, what is S22? Let us assume this is a system. As the sound wave is coming from this side, it is also possible that the sound wave can come from this side, okay, from port 2. Then when it hits, it can come back here. Now when we are talking about this sound absorbing object, it can be of a different profile. Now imagine that one side the profile can look like this, like a spherical stuff. Okay, on the other side, it is possible that it can have a triangular profile, something like this. So it means that even though the same energy is coming in, the reflection from this geometry will be different and the reflection from this geometry is different, right? So this side is characterized by S22 term. And another one is that when the wave is coming from this side, let me take some other color. When the wave is coming from this side like this, some amount of energy is transferred to this side. This is calculated as S21, okay? And same thing is applicable here. When the energy is coming from this side, some amount is transferred here. This relationship is termed as S21, okay? So now what we are going to do, we are going to model two, let's say this duct is like this one duct, and this as another one duct and another duct here. Now we don't know the exact details of this element. We don't know the geometry and the material property of this element, but we are going to describe all these transmission, reflection, everything in terms of this matrix, which is called as S matrix. Okay, so now let's take an example that is given in Ansys help manual. Let's go here. Let's go and find. Once you go in under mechanical APDL under acoustic analysis guide, you will find this example transfer admittance matrix. Okay? There is a difference between the S matrix. What I'm describing here is called the S matrix, but there are many matrices like this exist in the world. But basically, this whole theory is coming from mostly a network theory that is commonly studied by electrical engineers or the microwave engineers. So basically, what we are trying to say is that we are in the electrical terminology, we will relate the voltage and current, but in acoustics, we are going to relate the pressure and the velocity. Okay, but the concept remains same. So now there are many matrices like this. There is something called the S matrix, H matrix, T matrix, Y matrix, Z matrix, and ABCD matrix. But it all relates with the transmission and the reflection of energy between the incoming port and the outgoing port. And also there exists a relation between all these terms. So if you know one matrix, it is possible to back calculate the other matrices and so on. Okay. Now coming back here, let us take in this particular scenario, we have a system something like this, a micro perforated plate, but we don't know the finer details of this, or a foam. Let's say we don't know the finer details of what is the geometry and other thing. But what the manufacturers say is that this plate has a transmission loss of some dB. Let's say somebody is saying I have a transmission loss of 20 dB. What this means in the sense, when the energy, the acoustic power, the wave is coming with some power P1, when this acoustic wave crosses this medium, it will see a reduction in power of 20 dB. That's what that is what it means. Okay, so as long as we know this quantity, now it is possible to model, mimic the sound transmission loss exhibited by this physical device in a numerical way. To do that, what I am doing, let us take a simple case of not this. Let me take a simple case of this. Okay, so there is a pipe like this. Duct. In between there is the sound attenuating device. This can be any device, but I don't know what is the finer, what material it is made up of and what is the geometry of it. But the manufacturer of this device told me when the plane wave cross this device, it will show the transmission loss of, let's say, 30 dB. If I want to model this, as we have seen here in this place, the S21 is the term which is responsible for the transmission loss. Okay, among the energy that is coming in, how much energy is going to get transmitted? This is port 2. This is port 1. So S21 determines the ratio between the power at outcome power at the output port 2 due to the input power at port 1. So now we know here that we need to mimic a required transmission loss of 30 dB. And also there exists a relationship between the transmission loss and the coefficient T21. Once we know how much transmission loss we need to achieve, then it is possible using this equation possible to back calculate what should be my S21 term. And also, if we kind of assume that this device will show the same transmission loss from this direction, from this direction to this direction, or from this direction to this direction, then it is called a symmetric device. Then the term the term S21 and S11 are symmetric. We can use the same thing. Once we know the S matrix, then it is possible to transform this S matrix into a ABCD matrix. Yeah, here is the relationship between the S matrix and the ABCD matrix. The J naught is the characteristic impedance of the medium. Now we are assuming the air. The air is having a mass density and the speed of sound, so that we can calculate the ABCD matrix. Once the ABCD matrix is known, then it is also possible to calculate the Y11, Y12. This is called transfer admittance matrix. That is what Ansys is going to accept this as an input. So sometimes this is depending on what your S matrix is. This term is going to be a real or a complex term. Now we know there is these are all the Y11, Y12, and so on. Let's take an example that I have already set up. So to set up this problem, what I have done is that this is my entire acoustic model, and there are three regions. This is my incoming duct, this is the outgoing duct, this is the small device. When meshing, one requirement, this mesh is called the element that is used to represent this device is called the trim element. Okay, so this one requirement of modeling this trim element is that this region has to be of only one single element thickness. The actual device may be of any length. Okay, let's take for example, we have a duct here and another duct here, and this device is of some arbitrary shape. It may have any shape like this, some arbitrary shape. But when we are modeling this in a finite element approach, we don't want to model this as for whatever actual length. Actual length doesn't matter because we already know what is the transmission loss. The way to model this is just model the incoming duct and outgoing duct, and in between you mesh one layer of element that represents the trim element. These elements outside can have any number of elements, that doesn't matter. Okay, these can have any number of stuff. It has to be a connected mesh. The only requirement is that here you should not mesh this region with more than one element, something like this. Don't create a fine mesh. One layer of element is enough. That is one of the mandatory requirements. So once this is done, then what we have to define is we have to define the ports. Say for example, in this case, I have to define two ports. Insert acoustic port. Let's say I have to, let me hide all these bodies. I will keep only this body. This is my incoming port face. This face belongs to this body. Okay, and I have to define one more port, that is the outlet port, this face, and this also belongs to the same body. Okay, and once this is meshed, then we need to insert the admittance, transfer admittance matrix. Here we have to say which port corresponds to incoming, and or in other words, we are going to say this entire matrix belongs to which two surfaces or which two ports. We are saying between these two ports. Okay, so I have to say here my incoming is port 1 and outgoing is port 2. Then this has the coefficients. What we have to do is we have to put these coefficient inside this. For example, let's take this. I will keep this aside and I will bring this side here. So this is y11. It is only the real term. So we have to use only the real term, the imaginary terms 0. This is y12, imaginary term 0. I'm not going to discuss what is this alpha, probably in some other time. And same way, y21, the real part, imaginary part 0, y22, the real part, imaginary part 0. But there may be a situation where for example, this case, the y11 is real. I will show you another example. The y11 is real, the imaginary part is 0, but y12 is having both real and imaginary part here, right? I hope you can see that. This is a real part and this is the imaginary part. So you have to put real and imaginary part here. Okay. Now, this is how we kind of feed in we will represent the acoustic attenuating device somewhere here. Then this is the impedance. As I mentioned earlier, this impedance boundary condition can be applied on the exterior surface. So we cannot use this impedance boundary condition somewhere inside the domain. That is not possible. Okay, but it can be used. So in order to specify this impedance, now what I'm saying is that we are stopping it here, but I'm saying the medium aside this is also air. Here is the air medium, which is having the impedance of rho of the air multiplied by the velocity of the sonic speed of the air. When I say this is also having the same impedance, it means that the duct is open. Okay, it is not closed. In other words, it's an anechoic termination. So I'm using the impedance boundary. I'm giving the impedance value. This is only a resistance term. Value same as rho of the air multiplied by the sonic velocity of the air. As we can see here, 417.45. Other words, this can be mimicked or by inserting the radiation boundary. The radiation boundary, what it is going to do is it is going to do exactly the same, but it can internally calculate what should be the value of this resistance term. That's all it is going to do based on the material that assigned to this surface. It will take what is the rho value and what is the sonic speed and multiply and assign that. I have also defined two more ports to calculate the transmission loss. The first port is at the inlet and the second port is at the outlet. Okay, so again, in order to calculate the transmission loss, I have given some velocity here. In this case, I have applied acoustic velocity, but in many cases, if you are modeling a vibroacoustic problem, this velocity can come from your structural surfaces, so whatever it may be. Okay, so this is my inlet port and this is my outlet port. So upon solving this, we can go and calculate the transmission loss between the port 11. Port 11 is this and port 12 is this. Okay, if we calculate the transmission loss, we will get somewhere close to 30. Okay, and if you kind of look at the sound power level at the inlet, because for the given velocity at this surface, the sound pressure is 90 dB. But if we look at the sound pressure at the outlet level, it is just 60.9. There is a considerable amount of reduction. The sound pressure level may not exactly match with the 30 dB reduction what we planned, because transmission loss is always calculated in terms of a power, not in terms of the sound pressure level. But we can go and see the sound pressure level plot across this. You will see this being a straight duct. If there is no this sound attenuating device in between, whatever the 90.97 dB we see here, the same will happen along throughout the entire length. Okay, because of this attenuating device, there is a reduction in the things. Okay, this is the way we have to model that. But another thing we can observe here is that this term, we assumed S11 and S22 are 0. So what it means in the sense, whatever the energy that is coming in here, it is not getting reflected back at all. Okay, it is not getting reflected back at all. For this particular case, what I have considered is, I have let me see if I can show this. Okay, so at this inlet, I want to apply a unit pressure. Okay, unit pressure I want to achieve, but in Ansys acoustic analysis, the pressure is one of the degree of freedom. What it means is, let's take at this point, this is a degree of freedom. If we are saying here the pressure is 1 unit, even though this pressure wave comes inside and reflects back, when this reflects back and comes back here, this pressure has to change, right? If we apply this as a pressure boundary condition directly, this value is fixed because the degrees of freedom is fixed, so it cannot change. In order to avoid that situation, oftentimes what we do, we don't normally apply this as a pressure. We will convert the pressure as a equivalent velocity. What the relationship between the impedance is pressure by velocity. In this case, we know the impedance, that is nothing but rho naught by C naught. We know what should be the pressure to be applied, and we can calculate V. That is how, in this case, the velocity is calculated as 0.003. Once we know the velocity and the pressure, we can calculate what is the inlet power. It means that it is not the total power at this point, because the total power depends on this is called the incoming energy or the incident wave energy plus the reflected wave energy. It is a combination of both. But the transmission loss is defined as the ratio between only the incident, not the total pressure at that inlet, only the incident power divided by the power which get transmitted here. This is a transmitted power. It is a ratio of these two. Okay, so we can calculate. I have done the hand calculation for the return loss and so on, and it does that. So when we kind of do this simple calculation, we assume no reflection is happening, but in reality that is not possible. Okay, if you have any device, all the phenomena will happen. Some energy will get transferred, some energy will get reflected, some energy will get absorbed, and so on. So if we want to model all these phenomena correctly, then we need to know all these terms correctly. Once we know all these terms, then it is possible to correctly model the reflection. It is possible to correctly model the reflection on the inlet side and outlet side, transmission from this side to this side, this side to this side, and so on. Once we know all these terms, then again use the relationship, back calculate the ABCD matrix, calculate Y1, Y2 matrix, and so on, and input all the constants appropriately, and calculate the transmission loss. So this concept is demonstrated on a simple model, but this can be extended to any complex thing as well. Say for example, let's take this scenario. Let's take this scenario here. Let's have an underground well, something like this. Underground well. There is a pump here. A pump is operating and doing something here. Because of this, the pump is vibrating. This is a ground level. So this is a ground level here. Okay, this is an underground well. So what happens is that the water is filled up to some level. Up to this level, water is filled, but above this, air is there. So I'm going to model a small region of a air domain, somewhat like this. Okay, so this region is filled with air. This region is filled with sorry, some gap. Okay, this region is filled with air. So my interest is to monitor the sound at these points. What we need to kind of model. But here there is a small acoustic. There is a mesh just to avoid all the dust and other things falling in. There is a small mesh acoustic, not acoustic mesh, whatever mesh, just to avoid the foreign debris going in. There is a small mesh is put inside somewhere here. Though this purpose may not be directly acoustic, but it is going to exhibit its own attenuating property and so on. Okay, so to kind of model this, once we test this mesh, take the mesh to a testing lab. They will test this in an anechoic chamber. They will kind of mount this mesh, something like in a mounting device. They will mount this mesh somewhat like this. This is an anechoic room somewhere here. There is a anechoic. They will have an anechoic room here, both the sides. They kind of mount this mesh here. Okay, and they will send a sound wave here. They will measure what is the pressure and sound power here. They will measure what is the pressure and sound power here. Then knowing these two things, they can give you, okay, what is the transmission loss? Sometimes the transmission loss can be a function of frequency as well. So once we know the transmission loss as a function of frequency, then we can go and feed in this data as a function of frequency as well. In this case, I have assumed that this is a constant, but we can model this as a thing. The way to model this is, model this bottom region, assign this with okay, sorry, you need to assign this with water, and there is a air here. This is the small split that is done to represent the transfer matrix. Okay, transfer admittance matrix. And look at this. This is the trim element. Let me show it in a better view. Okay, this region is the trim element region. As I mentioned earlier, only one layer of thickness need to be used. That's the requirement. But you can understand more about this by looking at the help manual property, how to model the transfer admittance matrix. Here is the requirements and the details about how do we model the trim elements to represent the transfer admittance matrix. I was also talking about the surface impedance. You can find the details about that somewhere here. Acoustics, not here. We have to go back to the user manual. Yeah, surface impedance boundary. Yeah, so whatever form, even though we are specifying the absorption coefficient, the alpha is what we give as an input. Depending on the surface we are scoping, it can calculate what is the characteristic impedance. Then it will use this formula to actually calculate the real part of the impedance. That's how the software is going to deal with it. So whether it's a transmission loss or the absorption coefficient, reflection coefficient, everything need to be finally converted in terms of impedance values. Okay, so this is make this domain as a water domain, and these two are air domain. This is also a air domain only. This trim region is also with material property of the air domain, because this material property is required to calculate its characteristic impedance. Okay. Then this is the open atmosphere. The boundary conditions used all are meshed with the acoustic region. This is kind of a radiation boundary because the waves coming in should continue to go to the atmosphere. It should not hit this boundary and reflect this back. Okay. And all other surfaces I have not specified anything, because if no boundary condition is specified, it will be considered as a rigid wall. Okay, no stuff is done. Then again, I'm going to calculate the sound pressure level at this location or at various locations. You can calculate based on the far field. It is not necessary to mesh the domain where we want to calculate. Okay, look at this. In this case, our mesh is only up to this, but still we can go and calculate the acoustic pressure here, or anywhere away from that based on the far field calculation. To do the far field calculation, I'm saying use only the pressure information from this surface to do that. This far field radiation surface is really not actually a boundary condition. It is not going to impose any direct nodal DO of boundary condition or its derivative like velocity. Instead, it will tell Ansys use this surface to calculate the far field result quantities. Okay, and there are 2 ports defined on this surface itself. No, the one port because it is from incoming, the wave is coming from this. Say for example, in this case, I assumed this surface is vibrating with some velocity, but instead of this velocity, one can impose any complex velocity profile coming from the structural analysis. So my wave is traveling from down to up. So I considered this face as my port 1 and the top face as port 2, and the transfer admittance matrix is defined between the port 1 and port 2. Okay, then we can kind of solve this problem. I have a result without okay, I don't know, probably this may not be valid, but let me show everything. I will solve this problem first without the I'm solving for only one frequency now, but it is possible to solve for series of frequencies. Just for demonstration purpose, I'm solving for 3 frequencies without imposing the transmission loss due to this attenuation device. Let's look at what is the sound pressure level at this mic. And also I have created 2 more ports. The one port is here, and another port is somewhere here. This is really not the correct way of calculating the transmission loss, because as per theory, to calculate the transmission loss between 2 points, let's say this is the duct, and in between we are going to mount some form of a attenuation device. As per theory, the theory calls that both the inlet and outlet of this measurement should be anechoic condition. Okay, it should not see kind of any reflection. It should be open anechoic termination basically. Okay, but in this case, here we are not seeing the anechoic termination because there is another medium as well. So this is not exactly correct, but for a qualitative purpose, we can use that. Okay, so you can see that there is some results we are getting something like, I will take 36 and 29, or even let's look at the mic result. It goes up to 92 is the sound pressure level maximum at the mic location. Now let me kind of bring in the transfer admittance matrix and solve that. I would expect this to kind of reduce the sound pressure level at this mic location. This is the way to kind of qualitatively check, but this involves quite a lot of details. So if somebody want to familiarize this and completely understand and represent these, somebody need to really go and learn the transmission line networks and need to understand the impedance measurements, what's the real part and imaginary part and all those things to correctly represent any physical device in the simulation. But however, my objective today is to just to give you the idea and how once you know the correct information, how you can use the software to model this stuff. Now you can see that the earlier the sound pressure levels was somewhat like this. At this frequency, it was 53, it has come down to 39, 92 has come down to 64, 500, it was 61, it has come to 33.16 because of the way we mimicked the transmission loss mimicked the known transmission loss of this mesh device. Okay, I hope this gives you some idea about how we can model some form of sound attenuation device depending on where they exist, whether they exist at the exterior boundary of the acoustic domain or somewhere inside the acoustic domain. Okay, so I hope this is kind of a introduction session. There is a lot to learn about two-port networks and what is the relationship between all these quantities, how to experimentally predict this. Then finally you can feed it and take advantage of the software capability. Thank you.